trying to understand Pommeau, who is trying to understand Lorentz's model. And he says, well, the essential feature of what you're telling me is stretching and kneading. So what I need to say is that if I have a piece of dough, I would like to have dynamics that first stretches it, and then the baker folds it in some way. And then I have it on a table and I repeat this operation. So that's what kneading is. And that seemed to be, when you look at Lorentz attractor and Rosler attractor, that's essential feature. What happens is that neighboring, if you start with a volume of points, the neighboring points get stretched along unstable direction and get really squinched along the stable directions. And then they come back where you started because, you know, it's recurrent dynamics, and then you stretch and fold. So that seems to be the main idea. Now, you know, what is it that stretches? So stretching means that I take some distance, some length, and I multiply it by some number, ax. And if a is larger in magnitude than 1, then I'm stretching. And what is folding? You know, I would like to take something, and I would like, if I square it, so if this is a negative part, and this is positive, numbers on this side are positive, when I square it, they both give me the same answer. They both map like that. So I would like to square, that will fold, and then I would like to do something with this. So I would like to center it someplace, let's say. So you stare at this idea. It says it's a nonlinear process. First nonlinearity is square, which is called parabola. From one-dimensional example, we know what it does. It stretches the interval and maps it in such a way that it gets folded forward in time, etc. So finally, he writes two equations, which I will no doubt write wrongly. So this is x and y. And the first one has a parameter a. And again, these equations will be wrong the way I'm writing them because I don't exactly remember it right now. So the correct equations are in the book. But the idea of Henon's model is that this A captures the stretching. So there's a parameter which where it's large. It's, you know, this A could be 3, could be 6, could be something, but it's large. It means you stretch the thing. And then there's another parameter, and that parameter turns out, when you compute Jacobian, this is 2 by 2 map, when you compute Jacobian, this parameter turns out to be minus the Jacobian. And what is Jacobian? Jacobian tells you how volumes change. So this parameter is the volume contraction of this original piece of red, and this one is measuring how far it goes. So that's the essence of a non-map. And now you go back. Please read the book on this one, but what happens is that map is that if you take a fixed point someplace and you look at its unstable and stable manifold, you think about it and you discover you don't have to look at the stuff that's outside. All right, so this is unstable, W unstable, and this is W stable. So it turns out that the border, the thing that I had before for this 3-disk problem, there are some edges of the strips. These are actually stable, unstable manifolds. And if you're outside of those manifolds, you're just being pushed away. So you will not stay there forever. So they're cookie cutters that take your dough and says everything inside of that line has a chance of surviving for a long time. Everything outside doesn't. And then you extend them a little bit and do the same thing as we did before, but the manifolds come back, etc. And you start producing the same picture that we produced for the, sorry, it's someplace in here. this kind of Smale horseshoe picture before, where what happens with this map is the stretching is strong enough. After one stretching backward and forward, you have 4 regions. But now their borders are infinitely precisely defined because they're stable, unstable manifolds. And that's something you compute. So these are not random squares someplace. They don't care about how your initial volume was decided. So if you know these guys, you have the borders. And that's now immensely powerful because now you start counting all possible solutions of dynamics because they have to be within these borders.